Thank you, Jenny, for introduction, and thank you, Erlindo and Lyndon, for agreeing to provide these talks for us today. I think they'll be very helpful for us to shape the discussion during the in-person part of the workshop. I'll first introduce Erlindo, and I'm really sorry, I'll have to read from the list to make sure I got everything right. So it may not be as animated as I wanted to, but I think it's important to give a background of the breadth of work that Erlindo worked on over the years. So Erlindo was originally trained as physicist and atmospheric dynamicist. His research spanned a number of related topics in the last decades, including dynamics of stationary and transit atmospheric waves, numeric modeling of Lake Michigan, estimation of fluxes of heat, momentum, and freshwater fluxes over global ocean, climate diagnostics, including aerosol forcing of climate, hydrological cycle of subtropics and Amazon basin, and data simulation. Dr. De Silva was lead developer for the physical space statistical analysis system at NASA, GEO's 4 atmospheric data simulation system, quick-fire emission data set, and the Goddard aerosol simulation system with GEOS. From 2014 to 2018, Dr. De Silva served as a science study lead for aerosol cloud ecosystems, decadal survey preformulation study. Currently, Dr. De Silva is a Goddard Space Flight Center Science Co-Lead for the Aerosols and Cloud Convection Precipitation Decadal Survey Reformulation Study. An interesting part about Dr. De Silva is that he spends a lot of his effort on promoting open science and open source software, and he's a key developer of the Open Grads project. Thank you for all this background, Erlindo, and here's to you. Please go ahead.
Thank you. Thank you, Sergey. Thank you for the organizing committee for inviting me. I was a little struggling in which direction we could take this presentation. And I decided to frame in the context of atmospheric processes, and that in particular involve aerosol, clouds, convection, and precipitation. Right? So I'm not going to talk about the process of the coupling between land or atmosphere or ocean for that matter. I'm going to stay within the atmosphere. So I'm going to do a brief overview what's the horizon in terms of models and observations, and I will then zoom in and highlight a few sort of key observance systems that I think it is important for aerosol clouds and precipitation. One is the next generation of geostationary constellation, the Earth gas satellite, and the NASA atmosphere observing system towards the end of the decade. And I will conclude with a few issues in aerosol data simulation and some of our experience doing Mirror 2. Jenny asked me to address a number of 7 questions. I have one slide while this trying to short answers to those questions that I'm for sure we can debate that for much longer than a single slide. Okay, so moving on here. Actually, we got my timer on here. Make sure I stay on track. So as part of the ACCP study, we had a workshop back in 2020, almost 2021, for a mission that we aim to fly at the end of the decade. We really would like to have an idea where our models are going to be, where data simulation is going to be. And so this is like here summarizes some of the consensus. Nothing is scribed in stone here, but cloud and storm resolving models would be originally from sub-kilometer to 1 kilometer. In global models, we've seen already many of those examples as part of those digital twin experiments and the diamonds, right, between 1 and 5 kilometers globally. In models with aerosols from sub-kilometer to 4 kilometers in a regional scale. And even for the global, we have simulations at about 1 kilometer already. Climate models, most likely, we're still going to be in a much lower resolution for 25 kilometers or so. And when you find models, it's scalable from one to another one. But what exists now, at least if you only stays in the atmosphere, is the new component, is the atmospheric composition, the aerosols, the greenhouse and reactive gases. as well as the land, biosphere, and what have you. So there are several advances in model physics with new Lagrangian and Bayesian models for replacing the old parameterizations and ever more increased complexity. And of course, to go with that, advancing data simulation and how do we evaluate those models are going on. But what's really the point here is the processes become more and more important as the scales collapse, right? As you get more and more, although we do not parameterize things, but now we have to make sure the processes that you before parameterized are now being resolved. So there have been major advances or in the process occurring in the observing system, from the geostationary and several sensors that deals with trace gases to more process-oriented missions by the end of the decade. So we'll sort of highlight a few of those in the next slides. The geostationary ring, probably that should have been the title of this slide. If you remember the SCIP, International Satellite Cloud Climatology Project, something that Aerosols championed for many years, used to be a one channel with a very old set of geostationary satellites. And right now it's in the process of being planned, the next generation of this satellite climatology. It's not really a mean, it's actually a time series, right? And when we launched the Meteosat, the MTG in 2022, the whole equatorial belt would be encircled by this sort of ring of geostationary. You're basically going to have continuous, global, coverage along, plus or minus, 50 degrees. And those new sensors, they are very much, if you're familiar with the MODIS, they are on the same sort of kind of capability. Allows you to do, cloud dynamics because of the delta T. If you're talking about process, the time variation that you obtain with the geostationary is critical. And cloud microphysics, you can do aerosol, properties, and you get a diurnally consistent, climatology of clouds in aerosols for that matter. What does it really matter for reanalysis, right? But although we do not have this class of sensors going back, but now you have this sort of intersection of advanced sensors that can be used to as a calibration transfer to correct some of the retrievals of the old one channel algorithms and calibrate so that you can actually hopefully have smart ways of using the less capable data that existed before. So another series of geostationary satellites are the so-called the geo air quality satellites. Unlike the typical geostationary that gives a ring, those are very much concentrated in very small regions around North America, Europe, and in Asia. And the reason being is basically a data rate, right? Because each one of those is a very high spectral resolution, sensors with coverage every hour. So basically, data is not collected over the full disk. Nonetheless, it provides you the ability to do trace gases, and you have bands from the UV to the with the O2 band. You can get information about particle structure or information about placement of aerosol plumes and what we have. So those are some of them are launched. The Korean JAMS was up in 20. Tempo hopefully is going to be up by the end of the year, and Sentinel-4, which is the European side, by the end of next year, sometime next year. And of course, those are all complemented by this nice collection of the LEO air quality satellites, since TROP-OMI and OMPS and all the AMI, some satellites from China. Okay, so the other, as we know up to now, if you look in terms of active sensors, Calypso CloudSat has been the main source of this data going on since 2007, I believe. It was 05. EarthCare is the very next active sensor, including a cloud radar and a LiDAR. and is expected to launch in 2023. Unfortunately, it is a UV LiDAR. It doesn't have the same wavelength as Calypso. There'll be a little bit of disruption of the climate record. Nonetheless, is going to be our next active sensor in space. EarthCare includes a LiDAR. It's a UV LiDAR, but it's also HSRL LiDAR. It measures the molecular as well, the particulate. You can actually separate the scattering from the particulate. Unlike Calypso, which is a backscatter LiDAR, it has a double band LiDAR, a radar. So like SAT. However, it has a Doppler velocity. You can now have some sensitivity to the motion inside the cloud, right? So something gives you microphysics. And it has a radiometer of which channels in the visible, the IR, so you can get aerosol and cloud properties. And you have a broadband radiation that you can now use as closure to once you retrieve clouds, you retrieve aerosols, and you can compute radiation and verify with the broadband radiation. Like many of those new missions, I used to be in the old days, if you remember, that the data would be launched, the satellite would be in space, and all you would have in terms of data simulation is an afterthought. And right now, EarthCare, I think CMWF is pretty much ready to assimilate EarthCare data once it goes up. A lot of simulations and OSSIs and observation operator development has taken place. So here's some slides from my colleague Angela Benedetti about their effort in assimilating EarthCare in the sense that both the cloud and aerosols needs to be synergistically assimilated. And the accurate location of those measurements will help improve the presentation of the cloud and the aerosol and how that affect radiation. And likewise, they will be using the broadband radiation radiometer to compute the short and long wave radiation. And first as a validation, but if you use it as a validation, there's nothing preventing you that for Dvorak contacts, you can use that actually to constrain the short and long wave radiation, therefore allows you a lot of closure to make sure what you retrieve of clouds and aerosols have some level of consistency. So that's very sort of exciting. So NASA just went in 2017. We got our new decadal survey, which recommended 4 new interconnected, core missions. Several of them surface biology and geology and surface deformation and change and mass change. They are not atmospheric. They're mostly surface and other components of their system. However, there were 2 very much interconnected missions. One is called for clouds, convection, precipitation, and another one for aerosols and clouds. And so for a total of 5 missions. The science team, as we start to plan for those missions and did a study, almost from the get-go, we decided it makes no sense to treat aerosols and clouds, convection and precipitation separately. So here's a quick summary of what the decadal survey called for those measurements. For aerosols, they called for aerosol properties, aerosol vertical profiles, and cloud properties to understand their effect on climate and air quality, right? Air quality became almost at the same level as climate. On the cloud convection precipitation, he called for a couple of cloud precipitation state, really the microphysics and the dynamics for monitoring the hydrological cycle and all the contributing processes, including all the cloud feedback. As you can notice here, those things, there was not necessarily any direct call here, at least in the summary, for aerosol cloud interactions. But if you read to the 700 pages of the document, you'll see the aerosols and clouds and the convection and precipitation. They are very much part of the same sort of couple, process. So the study completed last year. I'm not going to go through some of the details, but I would just sort of highlight here the main instruments that we're going to fly. We're going to have a radar. It's a multi-wavelength radar with a double band like CloudSat in the KU. similar to what you have in GPM, with Doppler velocity, right? So not only you get the reflectivity, you have also the internal motion inside the cloud, which is very much important to determine the dynamics. And the KU radar may also have a little swath. You're not talking about 1,000-kilometer swath, but to give you a little contextual information about the precipitation. There's here a multi-wavelength LiDAR. Here we are back having the same visible channels that you find in Calypso, and also an EIR 1064 channel. And that is again a HSRL LiDAR in polar orbit. I'll show you, there's another simple backscatter LiDAR that also is going to fly on an inclined orbit. It is a spectrometer that's meant for radiation measurements, similar to that broadband measurement that was made by EarthCare. And here, really, the intent is to measure radiation at the similar scales that you're measuring with the active sensors. A microwave radiometer, which is a big constraint on LiDAR retrievals, the same way that a polarimeter is a good constraint on getting information out of the LiDAR. When I say retrievers, you think about if you're doing an analysis or any kind of simulation. I'm really talking about complementary information content of those passive sensors and active. They sort of come in pairs, and they really work much better if you provide them simultaneously. Okay, so what is the AOS constellation? You're going to see the word ACCP and AOS. AOS is the new name that we recently adopted. And so we have now a constellation. Instead of separate aerosol and clouds, we have out two different orbits. There's a polar orbit, very much similar to what you have with Calypso and MODIS and the Aqua satellite, and an inclined orbit like GPM. That's an inclined processing orbit. It makes measurements several times of the day and allows you, at least in the mean sense, to have a characterization of the diurnal cycle. So basically, those two things together, each one of those orbits provide cloud, aerosols, and precipitation together, right? So those measurements are always synergistic. So what are the very first 5 errors? Is really the global observations of the vertical motion, right? Or in deep convection, particularly with the KU radar. The collocated dynamics of cloud and precipitation. Yes, there's a illustration in the right that microphysical properties are very much are associated with updrafts and downdrafts, and so that those cloud dynamics influence the microphysics in many ways, and having those concurrent measurements are really critical to understand the processes. Global profiles of aerosol properties now with absorption, type, size, and number. We had some of those retrievals from passive instruments. We're talking now having vertical profiles with a more capable LiDAR. And the evolution of cloud and processes, one of the instruments I didn't mention here, is a pair of stereo cameras. They are set apart a couple of minutes, so you can see the deepening of convection and the vertical propagation of the smoke plume. And of course, the inclined orbit allows you to make those measurements also at different times of the day. It really gives you a sense of diurnal variability. So in terms of data simulation priorities, much like EarthCare and CMWF, we are really very much committed to develop all the modeling data simulation capabilities prior to launch. And that means enabling in JEDI all the infrastructure for simulation of both passive and active sensors. And we're going to develop as part of the mission some key level 4 products, simulated products. And for climate models, simulators such as COSP, so you can instrument models, so you can make meaningful comparison with the actual measurements from the get-go at launch. Okay, Earth system data simulation. For this crowd, that's not something I have to explain much. With the different, basically system, the ice, the ocean, the chemistry. the reactive chemistry and the greenhouse chemistry, the land, process, perhaps including the biosphere and the atmosphere. And all of those, and I think as you go more and more into process resolution, that here was actually, you think about, I'll prefer to use P for process. It's basically you're going to have to be doing parameter estimation at the same time that you do state estimation. And I'll say a few more things next when I talk about the difficulty with aerosol data simulation. But again, the process modeling and with deep learning or any parameter estimation will be by necessity part of this framework going forward. So as I conclude here, let me just say a few words, quick words about aerosol data simulation. I'm doing in time, Jenny. I have a couple minutes here. One, what's the difficulty of aerosol data simulation is the state representation. You have multiple 3D concentrations of mass or number concentrations of beam size depending on the complexity of schemes. But typically you have tens to hundreds of tracers depending on what you have. So it's a large space state. You have emissions that also, it's a lot of uncertainty that needs to be estimated, simply biomass burning in dust and marine biogenics. Those are modeled, but there's a number of uncertainties here that is part of doing a long-term reanalysis. We really have to get a handle on all those emissions. Observation operators. Aerosols are not trace gases, right? You don't have absorption lines that you can write a precise observation operator. Size is a variable. You don't really know index of refraction. There's no such a thing as dust, right? Or single dust, depending on the iron content or the mineralogy of the dust. Nonetheless, in a lot of those models, we assume that those properties are fixed, homogeneous, and hold throughout the globe. And therefore, when you write observation operator this way, in which M is the mass that's actually transported to the model, those parameters are assumed constant. And you kind of got away with it up to now if you have one channel. But we're to a point now where we're really at the limit of what we do. And joint estimation of parameters in that observation operator is critical for us to make any progress as we go forward. Very quickly, observing system, AOD is a vertical average and is a vertical, also an average over multiple species. I'm talking about 5 or 6 emissions, depending on what you resolve. It's a very low observability, right? Very, very low. You can do a radiation simulation as long as you have passive sensors. It's the same conservation difficulty. You don't have too much information content. And vector scattering calculation that you need for, especially as you go into UV, is very, very expensive, really. PM 2.5 is an important measurement, but really plagued by representativeness in single level as well. The LiDAR measurements provides you more and more information in the vertical, but it's a curtain, right? There is no coverage. So it's still another 2D measurement just in the vertical in a curtain. So a lot of, in Meta2, we use a VHRR for the previous data, use Miser, Aeronet, and the MODIS Aquintera was the main observance system that we use. Aeronet, we like to think is the radiosonde of aerosol science because it's a very precise station. It's not really, the coverage is not as good as it seems to indicate here because they are all not concurrent. But that's basically what we use in bias correction schemes to anchor some of the measurements into something that's relatively unbiased with respect to the Aeronet. So that really provides a very effective means of homogenizing the observing system, at least for the optical depth measurements. And data is available as the demise of Aquintera satellites in the next few years. Here's what we're going to have in its place. And the TROP-OMI provides also good information with the UV channels. And the GeoRing I already talked about. The ocean color instruments like PACE, that's meant to be flown next year. It's also a very good aerosol instrument. It provides not one, but 2 multi-angle polarimeters. Yeah, another polarimeter on the METOP second generation in the AM, and the active sensors that we were talking about. So we're going to really be well served in the years by the end of the decade of measurements that allow us for the first time to constrain processes of aerosols, clouds, and precipitation, including cloud dynamics with Doppler. So that's all that I had. I had here some answers to the 7 questions, but I think I'm out of time. I'll leave you with that, and I'll take questions.
Thank you, Erlindo. We do have about 3 minutes, so maybe we'll take one question for Lyndon. We'll move to Lyndon, and there'll be a time after both talks to follow up on any detailed questions, if those still stand. Any questions from the audience?
Looks like Ron has a question.
Go ahead, Ron.
Thank you, Chancellor. Thanks, Erlindo, for agreeing to do this and for giving us a nice talk. I imagine some of the work Virginie's been, Bouchard's been doing in the JEDI system, expanding the capability we have now for multiple wavelengths and kind of opening doors for new observables. I assume, other than just the AOD we've been at 550 that we've been assimilating, I assume these will open the door for things related to AOS. Is that correct?
That's true, Ron. But one of the things, that has all the basically the foundation to build upon. We will need to build observation operators for the advanced LiDARs. We don't have anything yet, but that's more on the cloud side for radars, right? So we're going to need to build some of those. But I think the foundation is there for the multi-wavelength and for ways of also to introduce the polarimetry, which we haven't yet developed much. But I think the foundation JEDI is very solid for taking that forward.
Well, what about more in the near term then? You mentioned all the work that the center's done being ready for, say, Earth Care. Will any of this work be usable for Earth Care? Because at least from my vantage point, you'd know better, I don't know any effort that any of us has been making with Earth Care right on the horizon. So will we be able to take advantage of some of those obs with some of the work we're doing?
Yeah, we should be able. I don't know exactly how they are building the observation operators these days, RTTOVs or some of that, So, but hopefully, we can leverage some of that effort and transpose that to JEDI, right? So that's basically where we need to have implemented, because not only for us at Gmail, Ron, hopefully that opens the door to any of our, JEDI community.
Yeah. Thanks.
Thank you, Erlindo. Thank you, Ron, for your question. Let's move to Lyndon. I'll pull up a biography. And again, sorry for reading from the piece of paper. It's not very smooth, but that's what I have to do. Dr. Lyndon Ashcroft is a lecturer in climate science and science communication at the University of Melbourne, Australia. Lyndon uses pre-1900 documents and weather observations to explore the climate of Australia's past, shedding light on historical climate variability and extreme weather events while improving data coverage for the Southern Hemisphere. She has previously worked as a climatologist at the Australian Bureau of Meteorology and a senior researcher in the Center for Climate Change at the University of Rovira i Virgili in Catalonia. Lyndon is a regular on a community radio, gives frequent public talks, and receives 2020 Australian Meteorological Society Science Outreach Award. 2021, she was selected as a Victorian Tall Poppy by the Australian Institute of Policy and Science for her excellence in scientific research and outreach. I would like to add a couple of words, saying that both Erlindo's talk that looks forward into advanced sensors and Lyndon's talk that looks backwards at available historical observations are really interesting when we contrast them together. And the challenge for the workshop will be to try to reconcile how reanalysis is a product that kind of sits in the middle and lose the two perspectives. So with that, Lyndon, please Go ahead.
Sergi, that's a really insightful point. I totally agree. Many thanks for having me, and thanks for the organising committee for inviting me. Hello from the future. I'm talking to you on Wednesday morning here. Just before I get started, I wanted to acknowledge the traditional custodians of the land on which I'm speaking to you from today, the Wurundjeri people from the Kulin Nation. Pay my respects to their elders, past, present, and emerging, and also extend that respect to any First Nations people who are here today from around the world. Let me just share my screen. We are having a bit of a change of pace now from what Erlindo was talking about. Let me just move you guys over here so I can see you. Please let me know if you can't see my screen. The brief, the message, the name of my presentation is Sparse Data Rescue, and I love this image from 1890. This is from southeastern Queensland, where there was a series of floods in the early 1890s that devastated the town of Brisbane. This is the brewery, the West End Brewery, which is sadly no longer open, but breweries flood pretty much every time it floods up there in Brisbane, including this week, just gone. There are currently floods occurring all the way along the eastern coast of Australia. La Nina plus a lot of consistent onshore flow, atmospheric rivers, it's all combining to make a perfect storm of really extended wet weather. And we've had casualties, millions of dollars worth of damage, tens of thousands of properties, uninsurable now moving forward. And I think it's important as I go back in time to remember that these kinds of historical events and this kind of historical information really still has its value in comparing what's happening now to what's happened in the past. And obviously that is such a crucial aspect of why we use reanalysis. But sometimes for me, when I get lost exploring these 19th century stories, it's important to remember that we really are trying to get a context of what's happening now so we can plan for the future. As Sergi said, I work mainly in the Australian region, and so what I'm going to talk about today are a few kind of case studies, mainly based in Australia. I guess I'm also representing the global atmospheric circulation reconstructions over the Earth initiative or community, which is a band of people who do this work, this data rescue work, all over the world. You know, just like most data-based activities, it doesn't get a lot of funding. It's not seen as very sexy by people who organise money for research, but it's such a crucial aspect for understanding our weather and our climate. So let's break up these terms into a couple of different points. I want to look at data rescue first, and I kind of thought, what do we mean by data rescue? I probably don't need to explain that to those of you here, but just in case, let's think of it as the recovery of data from a non-usable format to a state that can be used for scientific analysis. Okay, so that doesn't always mean rescuing handwritten chicken scratchings like the ones you can see here on the right. It can mean rescuing something from an old digital format. It can mean rescuing something from a graph, all sorts of things like that. And it doesn't just mean finding the information. It's also about imaging it, extracting that information, transcribing, quality control, that whole process. It's time consuming, it's messy, it's laborious. There are missing data points. There are changes in formatting. There are changes in units. There's changes in handwriting. There's changes in observers. There's changes in all sorts of things. You know, the size of the data set is smaller than if you were using information from a satellite or using output from a supercomputer, but that doesn't, so you don't have that problem of size to deal with, but you do have the problem of complete inconsistency and chaos that you often have to wrangle into a format that can be used. But I would argue, in some respects, it's a cheaper way of getting new data into our global climate data products. It's cheaper than launching a satellite, it's cheaper than building a supercomputer, and it exposes a lot of new information that we need to understand our atmosphere and ocean behaviour. It's also quite a valuable tool for engaging people with climate science and meteorology. So we've seen a suite of successful citizen science projects, particularly during the lockdowns of the last couple of years, people stuck at home and able to contribute to climate science by rescuing observations. I really like this quote from ECMWF. that data rescue is not just about discovering and digitizing data, but bringing those data together in a consistent way and making them available to all. It is a huge task, and that making them available to all is something that I've been thinking about more and more, because a lot of the data rescue activities, particularly as we go further back in time, when we look at some really old observations, they're quite done on a regional or a national level. And there are more efforts now and coordination between different activities in Europe and the US to sort of bring those things together. But that final hurdle in some respects doesn't often get there. People think, oh, I've digitized it now, so it's okay. And it's that final step to get it into global data sets that I think we really need. So as I said, data rescue can take many formats. Sometimes it's in a CD. I've heard of data rescue happening because someone had it on their computer and they thought it had been lost for a while, and then it was recovered on an old laptop. Is that data rescue? I don't know. Some people think it is. Maybe it's on a floppy disk. Maybe it's a bar graph chart. We've seen rescuing happen that way. Or maybe like this image on the bottom right here, there are weather observations that exist in graphical format. This is a map of Australia in the early 1900s. You can see in those tiny little red and black handwritten pieces there, they're pressure observations that volunteers here in Australia have painstakingly digitised and submitted to the International Surface Pressure Data Bank to improve future versions of the 20th century reanalysis. You can imagine just how much time and how much eye straining it would have taken to do that. Data rescue also can seem like a process that doesn't have a timeline on it, but in reality, you know, archiving weather observations is something that happens or has a different priority depending where you are in the world. You know, some countries, weather observations are organized like this, and others look a little bit more like this. You know, and heaven forbid you had weather observations that were in a flood-prone place, or were affected by an earthquake, or were affected by volcanic eruption. So there really is an urgency to some of the data rescue that we do around the world. And maybe when you're thinking of data rescue, possibly those of you who are familiar with it might think of data rescue. I'm largely talking about the land today, but of course there are lots of weather observations that are in ship logs and moving sources of information, and old weather is the best example of this as a citizen science activity that's provided hundreds and thousands of observations for reanalysis and for understanding of past climate variability. I think it's just a beautiful image as well. I wanted to share it. So that's kind of what we mean by data rescue, rescuing observations from a state in which they couldn't be used for modern science to a state in which they can be used for modern science. And that includes getting all of the information that we can about the data as well, how they were taken, who took them, where they were taken, were there any changes, all of those kinds of things. Now let's talk about the word sparse, right? Sparse data rescue. Because a lot of the records that we've been talking about in the series so far, it's been a great collation of information and experts who use reanalysis in different ways, but a lot of that's been talking about, you know, the 20th century. And when we talk about sparse, I guess it can mean a few different things. The first would generally be, okay, there's not a lot of data in space. This graph here is the number of pressure stations that are contributing data to the International Surface Pressure Data Bank in 1788, which is the year that Australia was invaded by the British. And you can see there are 3 dots, including one in Australia, which was a First Fleet astronomer who took observations for the first 3 years when there were white people here in Sydney. But even if we go up to 1860, we've got a few more dots. Those of you in the US, look at you, so lucky. Look at all those red dots. Quite a few in Europe as well. Still only 2 in the entire Southern Hemisphere. So the sparsity there is quite distinct. And then even if we go to somewhere like 1950, where there's red dots all over the place, a lot of observations, and our confidence in 20CR is a lot probably greater than for lots of different things, even in the Southern Hemisphere. But if you look over kind of in the Pacific Islands here to the northeast of Australia, there's no dots at all, right? There's nothing. It's not until about 1970 that we start seeing some coverage there. So that would still be considered sparse data rescue if you're trying to rescue observations from that part of the world at that time. Obviously, as we go further back in time, there are fewer and fewer observations. I just took this plot from Tim Osborne's paper about Crew Temp 5, looking at the number of observations that contribute to Crew Temp 4 versus Crew Temp 5, the global temperature data set built there over in the UK. And as you go further back in time and as you go up and down in the latitudes, you can see there are fewer and fewer observations. So you can think that generally going further back in time, the data are more sparse. So you've got fewer stations to work with, which means every record that you can find is more valuable, but also assessing the quality of those data is a little bit trickier as well. And I want to talk about that in just a little bit. And then another component I was thinking, what do we mean by sparse data? What does that actually mean? Another thing to consider would be variables, right? You can have observations, a beautiful map covered in red dots to say, look, we've got all of these pressure records around the place. We've got all these temperature records around the place, but okay, what about wind? Oh, we don't have any wind that are available for modern analysis, right? And I wanted to show this as an example because I think this is a really interesting case where the limits of large organizations to recover observations because of budget constraints mainly and having to prioritize means that data rescue activities that are done by volunteers or done by small scale organizations can really make a big contribution. So on the right here, this screenshot from the Bureau of Meteorology's website shows the amount of data that are available for a station in New South Wales, so about 10 hours north of where I am today in Melbourne, at a place called Armidale. This is an area that was devastated by drought a few years ago. Australia, it's never a dull day here. It's either droughts or floods or heat waves or bloody snowfall. It's all happening. But these are all the observations you can get publicly from the Bureau of Meteorology. Only rainfall. They've got the daily rainfall observations from this station, and that's it. The image at the bottom right there is the man who took those rainfall observations. His name is Algernon Belfield. He was a grazier, so he kept sheep on his farm. He wasn't paid, he wasn't trained, he was just really interested in the weather, and he kept observations every day for about 40 years until shortly before he died in 1922. And his grandson, who sadly passed away last year in his 80s, him and his wife found Algernon's weather journals almost 10 years ago now. And in those journals is much, much more than rainfall. There's temperature, there's wet bulb, there's dry bulb, there's pressure observations, which are now thankfully in ISPD. There's wind information. There's remarks as well about snow, about frost, about all different sorts of things like that. So this is a time where we have observations in Australia. We have observations in the Southern Hemisphere at the turn of the 20th century, but we don't have a lot of observations of all of these variables. And so it fell to a group of volunteers, retired historians and students who were hoping to gain the experience to rescue all of these data. And then we were able to do some quality control with them and say a lot about the climate of this part of the world, and also provide this information to international models. Ironically, the tripping up point for us is trying to get this information back into the Bureau of Meteorology here in Australia. There's a lot of paperwork that needs to be completed before that can happen. So these records are now contributing to international things, but not increasing that information there that you can get from the Bureau's website. Anyway. So that's kind of what I'm thinking about when I think about data rescue and sparse data. And I'm really looking forward to discussing what that means for you when I finish here. But then I wanted to ask this question about how we can trust sparse data rescue, how sparsely rescued data, how we can rely on this information, how we can use it. It's taken in a very different way to the flux data that we get from satellites and the observations that come from buoys or the observations that come from modern instruments, but we need them. We need them if we're going to provide century and longer representations of what our atmosphere was doing and see really how much things have changed. So I kind of thought I'd go through 4 or 5 different techniques that I think are used not only by me, but by other people who work in this space around the world. And the first one to think of is by rescuing as much as we can, right? Thinking about that example I just told you, it's really the ability to be able to compare as many variables as possible from any data source that we come across that can help us gain a full picture of how much we can rely on these really old observations, or these observations that kind of exist in a vacuum without anything else to compare it to. If you've got data in a really rich network, then you can compare it with a lot of neighbors, or you can compare it with, you know, overlaying satellite information. You can compare it with various other independent sources, but we don't have that luxury when looking at sparse records. So we have to be, if we can afford it, rescuing as much as we can. As I said, citizen science can be really helpful here because one person's variable that they don't care about is another person's variable that they really care about. And we've seen that a lot with ship data rescue, where some people are really interested in the historical aspect of what a ship was doing as it was passing through that strait, you know, on its way to war. Whereas other people are really interested in the winds that were experienced or the pressure variability. And that allows different contributors to extract what really matters to them. This picture on the right here is actually Algernon Belfield's weather station on his farm. And I put that up as an example because at the moment I'm working with those records to understand droughts in New South Wales back to 1880. And I'm interested in understanding how temperature extremes are changing as our droughts are changing as well. You know, whether we're seeing more, I mean, presumably we are, but looking further back in time, the relationship between extreme cold and hot temperatures and droughts here in Australia. And I wanted to look at frosts and snow because this part of Australia experiences some quite cold extremes. And thankfully, we digitised all of Algernon's records. So when I looked at his remarks about frosts, I was able to cross-reference his written records with his quantitative temperature information and provide a more reliable analysis of how many frost days had occurred, because he actually wasn't that good at writing down frost when a frost occurred, but his temperature observations. Thanks to statistical analysis, we did a fair bit of assessing of the diurnal cycle and the seasonal cycle, and we realised that his temperature observations, for the most part, were pretty good. So we were able to use those with a bit more reliability. The next thing you can do if you're working with really sparse data is really try to find some neighbours if you can and make use of them, even if they're really far away. So this is an example from a while ago now, looking at pressure records that were recovered for the east coast of Australia back to the 1840s. And there's fairly good agreement there, which you probably would expect. You wouldn't see that level of agreement with temperature, but with pressure, the month-to-month variability is really similar for all of those stations, except for one, which is this one here. This was Port Macquarie in the northern part of New South Wales, which is the area, one of the areas that's currently underwater. And most of the observations taken here were taken by convicts. So these were people who were white-collar criminals who were brought over to Australia to serve their time. And a lot of them were trained as meteorological observers and approached it diligently, but obviously the observer at Port Macquarie was less reliable, was less diligent. So once we had assessed this relationship, we had unfortunately removed this data set from further analysis. The next kind of comparison you can do, obviously, is looking at qualitative data. So you want to find some other information that can help support the results you find. And this becomes particularly important if you're looking at extreme events, I think. So this is an example of rainfall, monthly rainfall in Sydney from 1840 through to 1855. And you can see there's 2 big peaks of rainfall there that I love showing this graph because I made it during my PhD. And at the time I thought, oh, I've made a big mistake. Oh no, my supervisors are going to be so annoyed with me. But once I cross-referenced it with newspaper accounts at the time, I realised that actually both of these events were very severe rainfall events. They were really extreme, more extreme actually than the current modern record for the wettest day in Sydney. So both of them were associated with pages and pages of reports in the newspapers about flooding, about houses being damaged, about people being washed away, about the governor and his wife going to a show in a horse and cart and the horse and cart falling into a big puddle in the middle of the street. And the actual original data sources themselves both showed that in the end, over 600 millimeters of rain fell in about 24 hours. Do we trust that exact value? Maybe not. We need to know a little bit more about the nature of the instrument that was used, but we can see, particularly for this event in 1844, the poor observer had to keep emptying the rain bucket because it kept overflowing. So there was a fair bit of care being taken in these observations. It's also useful for extreme temperature values. So this is a picture of a zoo in Adelaide in the late 1890s when there was a lot. And in 1897, this is from a recent paper that I've done with some colleagues looking at extreme temperature in the southern part of Australia back to the 1830s, using some sparse records that we've recovered from amateur sources and from published data sets as well. And the instrumental data suggested to us that it was really hot, right, at the turn of 1897 to 1898, the last few years of 1897. There were temperatures above 40 degrees for 5 days in a row, and the overnight temperatures didn't really drop below the mid-20s. And this was verified again by the newspapers. According to the papers, at least 65 people died. And I put this picture here of the zoo because a lot of animals passed away as well during this heat wave. So we're able to use this qualitative information to verify our quantitative information. And we did that for all of the heat waves that we identified numerically before 1900. And I think it was about all but one of them were associated with accompanying newspaper reports. So we were able to say with a bit more confidence that the number of heat waves we're experiencing in the southern part of Australia are increasing, which is a result you found in modern data, but now we've got 17 more years of instrumental records to support that. Another thing that we can do is to use intervariable relationships. And this, again, you probably think that you probably know all this already, but I think it's worth just like stepping through the different aspects that are important when it comes to rescuing these observations and the sorts of relationships that can be useful when you're trying to assess what you can say and what you can't say using these historical weather observations. So this is, again, another recent publication looking at observations in Adelaide in the southern part of Australia. And there are observations there that were taken using two exposures, using a Stevenson screen and a glacier stand for about 40 years. It's the longest parallel temperature data set that exists in the world. And we use that information to splice it together to build a more reliable temperature data set for Adelaide back to 1859. But you can see up here in the maximum temperature values before about 1872 that the temperatures are pretty high. Now, it was a dry period in Australia during that time, so maybe it was really hot and maybe it was warmer than average, but we were a little bit suspicious. So we did a fair bit of cross-referencing by trying to figure out how the temperature, the maximum temperature in the modern period relates to rainfall variability, to cloud cover. We don't have cloud cover all the way back that far, although we do have some cloud records. But we were able to establish that the relationship between the rain and the diurnal temperature range is much higher than we would kind of realistically expect. And the amount of cloud that was needed to create such a warm temperature anomaly hasn't been recorded before. So we do still think there's some inhomogeneities because we've been looking at this relationship between the two variables.
Start wrapping up.
Yep, sure thing. We can also compare with paleoclimate reconstructions, and sometimes they agree and sometimes they disagree. Finally, of course, we can use reanalysis. Reanalysis is such a vital tool in a data sparse area to help us provide some independent calibration. But is it independent if we don't have many observations and all of those observations are then going into their reanalysis data set? So I have a few examples here to show that we can do it all the way back to the mid-1800s in southeastern Australia and southwestern as well, which is really exciting for us here in the Southern Hemisphere, where we're just sorely underrepresented in so many of the global data products that are used. I'll leave it there. I really enjoyed working with these questions as well, and my answers are quite different maybe to other people, because I'm thinking about, for us, using historical, looking further back in time, that information. Integration of new data is so exciting for us, and the ability to assess uncertainty and the reliability of our reanalysis products through the use of the ensembles is so valuable for us down here. And it's really exciting, as I said, to see more international collaborations, combining regional data rescue activities with global data rescue activities. So I look forward to the conversation after this, and thanks a lot for having me.
Thank you, Lyndon, for your presentation. Let's see if there are any of the audience who have questions for Lyndon. Laura?
Hi, Lyndon. Good to see you. Thank you so much. That was a great presentation. I really enjoyed it. And I think probably a different thing for a lot of our audience today. So that's great. I was sort of curious, given that we have, limited resources, but if you were in charge of determining the next steps in the data rescue community, like the next priorities, you sort of alluded to it, but a little bit more specifically, what would you say would be the most important focus, either in terms of specific variables or specific times or locations? My guess is you will say Southern Hemisphere, but I guess beyond that, do you have any any preferences?
Yeah, that's a good question. Hi, Laura. The Southern Hemisphere, obviously, I didn't quite realize, I think, when I entered this field, just how much is lacking in the Southern Hemisphere when it comes to, you see the uncertainty estimates using that kind of ensemble spreads and stuff, and they're so much larger in the Southern Hemisphere. Of course, right, there's a lot more ocean down here, and that makes a big difference. But I think the Southern Hemisphere, and also the developing world, but that comes in a few different ways, doesn't it? In some respects, maybe the data aren't there, or they are there, and it's not a scientific activity of rescuing. It's a political discussion about sharing, so I think that's really important. And I actually would throw the question back to the reanalysis development community to think, where are the places where you need the observations the most? What kind of observations do you need? We are in the state where we will rescue whatever we can find. We know that it's all valuable, but maybe it needs to be a bit targeted. Obviously, we would love to find an incredible collection of instrumental records taken by penguins in Antarctica that go back to 1800, but I don't really think that's going to happen.
Great, thanks. Yeah, I'm curious to see how this discussion will continue in the workshop, particularly as we look towards coupled reanalyses in the future, because this is obviously atmospheric heavy, which is fine with me for now, but in the future, I'm curious to see how it goes. So thank you.
Absolutely, yeah. I realize that I'm a little bit different from the other presenters who've spoken so far in this webinar. So thanks again for having me on as part of the series.
I'll have a quick follow-up to Laura's question, and I'll move to Jacob after that. So if we say, in existing reanalysis, surface pressure is one main observation we've been simulating. But there are other historic observations: rainfall, wind, some SST from ships. What do you think is the most underexploited data set of historic observations? Something that's pretty well recovered, high information content, but is not assimilated in sparse reanalysis right now.
That's a great question, Sergi. There's heaps of wind. There's so many wind records out there, and I know that wind is a very fraught variable. It's highly influenced by local factors. It is notoriously fickle and full of gusts and changes and those kinds of things. But I also know that the records exist for a really long time, the further back in time you go. And now that we're in a position where we have the computing power and we have the mathematical and the physical grunt to calculate different versions of what the future could be, I wonder whether a greater inclusion of wind might be helpful. Temperature is also useful, but it's quite fraught too, because the way that it has been taken has changed in steps. So if you've got neighbors and the thermometer exposure changed at all of those stations at the same time, that could really have an impact on the reliability of your resulting product. Yeah, I never thought I'd say that. I didn't love wind variables. I didn't love wind observations for a while. I thought, oh, they're not useful, but now I just think there's so many of them. They could be handy.
What is the state of precipitation data?
I think it depends on where you are and the resolution you're interested in, right? I don't know how useful daily precipitation data are if you're trying to construct a 6-hourly picture of what the atmosphere was doing. I know in Australia, we had a lot of money and effort put into finding rainfall data because that's the commodity that really, really matters down here, you know. Drought is really devastating and equally as devastating, and our multi-decadal rainfall variability is so extreme. But sub-daily rainfall is harder to find from my experience. Yeah, it is harder to find, but that's not to say that there maybe isn't kind of pluviograph information that could be accessible for the 20th century. I don't know if that would be useful. But rescuing that, like rescuing a graph, is a process. There's a lot of automation, and that's something I didn't talk about as well. There's more and more integration of AI and automated data rescue that's happening at the moment. Colleagues over at NIWA in New Zealand are really pioneering relationships with Microsoft and Google to try to improve the AI reading of these really old handwritten logs to help rescue weather data, which is exciting. That might be helpful. Yeah, I don't know. Don't know more than that. Sorry, Sergi.
No, that's good. Thank you. I'll just remind people that, of course, they're free to leave at the end of the hour, but we did block 15 minutes for the overflow, so we're in the efficient overflow section now. I will go for a question to Jacob, and then I also have some questions for Erlindo. Jacob?
Okay, yeah, thank you. Really enjoyed your talk. So recently I had the opportunity to work with some 19th century shipboard data, and sort of counterintuitively, I was actually impressed by how accessible it was, in that, if a physical copy persisted, then it was just tables and you could digitize it and use it in ways that were not anticipated when it was taken. And so I guess I wonder, as someone who does this all the time, whether you have or would care to speculate on things we ought to think about for our modern data sets, looking 100 years out in the future when people might want to try to use them. Are there lessons to be learned from data rescue for how we deal with our modern data?
What a wise question, Jacob. And you sort of assume that now we've got it all figured out and we already have that provenance in place to make sure our data are stored in a useful way moving forward. But yeah, the likelihood is probably not. I think my biggest takeaway from working with historical records is that it can be really hard to find the appropriate metadata. Like you say, it's really, you can find ship logs and they are quite clear to read and clear to follow. And even if you're looking at land-based observations, sometimes you'd get an observer, and I think this happens in Canada as well, that would get sent, probably all over the world, get sent to the central place where all the data are being stored, and then there would be some corrections applied. And if you're working with the original books, you've got these like black table of data, and then you've got a bunch of red numbers over the top, which can be quite confusing to untangle without some decent metadata associated with it. And I think it's really important, look, as it is with all data storage activities, to ensure that there's clear provenance and there's clear traceability to different versions, to any quality control that's been applied, and directing to any kind of supporting information that might be useful. And I know that there are lots of discussions about doing that on a global scale. Every country has its own process, its own fancy database, its own acronym for it. And I know that there is talk about moving everything into the same place. How possible that is given all the shapes and structures of observational data sets, I don't know, but hopefully maybe by the time we retire, it'll almost be in a place that the next generation can tidy it up. Not sure.
Thank you. Thanks.
I do have one question for Erlindo, but before I go myself, is there anybody from the audience who was waiting all this time to ask questions to either Lyndon or Erlindo? Okay, I'll go ahead with my questions then. It's not a very well posed question, it's more a discussion point. So the question that we're trying to understand, Erlindo, is like, what is this connection between Reanalysis activity and design of future missions? And one venue suggested that we can use modern observations of kind of coupled microphysics, clouds, aerosols to calibrate some previous measurements. Can you say maybe a little bit more about that? I think you're muted right now.
Yeah, I said something like that in the context of a SCIP, right? International Satellite Cloud Climatology. For many years, that's based on the old geostationaries, was one channel, right? There's only so much you can do with one channel. So what you can do is have in periods in which there is overlap, or you can take one channel and try to find ways to calibrate single, channel algorithms, and try to make sure, you can train. Actually, what I use for MERA2, I use AVHRR of the past. It was one channel, the 6-7 nanometer channel. And I basically use several other sort of predictors for that. I use some speciation coming from the model. I use some other things that I was able to train in the modern time when I had MODIS, right? So it's just sort of transformation of the old data, or bringing in additional empirically has to be done, factors to help constrain the retrievals that really can be done if you have a higher standard, higher quality data, at least for a period of overlap, so you can do some sort of calibration transfer, so to speak. So you certainly can do that, with aerosols. Maybe we can squeeze in some single channel aerosol data from the past by bringing not only that channel, but bringing probably some forecasts of speciation, some other characterization of, the surface or whatever have you. But I guess it's a little bit of, experimental, right? So, but again, it gives you that possibility, right, of make better use of what you had in the past.
So it's an interesting idea. So instead of, if in weather prediction, we try to use less retrievals and more direct radiance assimilation, you advocate that for reanalysis, you might actually want to do the opposite, because retrievals might bring information from a modern system.
Not necessarily. You can still do radiances for. The only thing that I said, there's a little challenge with using some of those measurements, is cost and be able to afford to do it. No, but I'm saying, for example, I used one channel, and that channel was and I used information from the model, some key parameters the model could predict, to help really, I use a neural net actually to get all the retrievals to be tuned against, MODIS. But, it's basically, if you have free parameters in whatever means we're using to extract the information from the old data, think of it as a bias correction, if you will, that, you need to have a training set, right? You need to have something that you can get the sort of empirical approximate algorithm trained. And that's what the future sensors give you, is a little bit more, of a ground truth, if we will. That's of course not a truth, but I think you can still use, radiances, but the aerosol problem, that's extremely, you constrained, right? So you don't really have information content. So, but no, I don't think you really. I'm still a big believer in using, radiances. But the only problem is when you cannot afford it, right? So that's where you still, if you look at Copernicus and what they still do for the trace gases, a lot of retrievals are still assimilated in the 34, right? And many, a lot of the reasons is cost too, right? Because you need basically vector radius calculations. Those things are not really, it's very burdensome on the 34.
Thank you. I guess maybe another clarifying question. So one thing you didn't mention if using reanalysis to inform future observance systems. Is there any comments you want to do about, possibility of doing that?
I don't think I understood. Could you repeat the question, Sergey?
So is there any ways and you can see how reanalysis as a product can be used to inform future observance systems?
Oh yeah, all the time, right? all the time, because we can really, you can use a reanalysis as for performing OSSEs, right? So especially, for example, people have done that in what they call climate OSSEs. I'm not going to go into the detail. I have a few reservations, some of how the things are done, but you can imagine that you have a reanalysis of multi-decade and you're trying to detect some kind of trend, right? Assuming you can believe the trend in the reanalysis. You can use that actually to simulate the radiance and simulate the measurements and try to make sure you can build an instrument with enough signal to noise to be able to detect, the trend by means of retrievals. For a lot of the missions to this day, well, it's a little bit of, social engineering, right? But a lot of the OSSEs, we did a lot of retrieval OSSEs, right? So we use a nature run to simulate radiances at the sensor footprint. And then, okay, so you think you can retrieve that parameter. Here we go. Here are those reflectances or backscatter from the LiDAR. And let's see what can be, retrieved. But I think reanalysis, especially if you're interested in this sort of detectability of trends and things, as long as you can resolve those, it provides you a very good sort of means of doing OSSEs.
Okay. Thank you, Erlindo. Well, probably it's time to wrap up our webinar. It was very thought-provoking to think about both ends of the observance system within the same hour. Is there anything, Jenny, you want to do to conclude?
Just one announcement. We're going to try to open up registration for the reanalysis workshop within the next month. So we'll have that posted on our website, and I'll try to share it out to all of your networks once that's available.
So it's going to be Jen, what's your thoughts right now? Is it going to be hybrid or virtual only, or?
Yeah, we are planning it for a hybrid event. So we'll be able to accommodate both virtual and in-person participants, hopefully.
Okay.
Thank you both speakers for your time.
Pleasure.
Thank you.